All right, maybe we can get started. Welcome back, everybody. It is my great pleasure and honor to introduce Professor Lieven Eeckhout. He is a senior full professor at Ghent University in Belgium. For those of you who know our very own Trevor Carlson, Trevor is Lieven's PhD student, former PhD student. So we are very glad to have, somebody from his team with us as well. And we're very glad that Lieven agreed to come to this CS Research Week. He's very, very well known as a computer architect. His most of the work that made a lot of impact are in computer architecture simulation, including the Sniper tool that probably some of you have been using. But today he's going to talk about sustainable computer science, computer systems design, which I think is a very interesting and emerging topic. Lieven has received all kinds of awards that's possible. 2017 ACM Cigar Morris Wikes Award, 2017 UPSLA Most Influential Paper Award, multiple, actually 5 IEEE Micro Topic Selection, Micro 2024 Best Paper Award, ISPAS 2013 Best Paper Award. He is IEEE Fellow, ACM Fellow. He has chaired many, many conferences, including ASPLOS, which is going to be held this March 2025, and he was Editor-in-Chief of IEEE Micro. And just on a personal note, he's the most amazing person that I have ever met in my life. So with that, Lieven, please.
Thank you for the very kind introduction, and thanks for having me. It's my great pleasure to be here and talk about sustainable computing. So to set the stage, when we talk about sustainability, what are we talking about? And I really like this quote from 1987 about sustainability. So it says, sustainable development is a development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Yeah, it's a very simple definition, but a very powerful definition. Yeah. So how are we doing? Well, we're not doing great, to be honest. Yeah. So you may have heard about the Earth Overshoot Day. So the Earth Overshoot Day is defined as the day at which we, as human beings, we have consumed all the resources on Earth that can be reproduced within 1 year of time. Yeah. And in the 1970s, that was around the end of December. So at that point in time, what we were consuming as humankind was sort of in line with what the Earth could reproduce. But over the decades, we've gone to a much worse situation. Today, it's around end of July, early August, when we are hitting this Earth Overshoot Day. So the amount of Earths that we would need with the current consumption would be 1.75 Earths. Yeah. So clearly, we are in a bad shape. Yeah. And this whole line of research, which I just recently started, was instigated by this observation, and the questions were like, what is the key contribution of ICT in this sustainability question? And is it growing? And can we do something about this? We are computer scientists, we are computer engineers. Is there something we can? And if so, we definitely should do something about this. So I've broken down this talk into 4 parts. The first one will be about what are the challenges if you want to do research in sustainable computing. Second, then, is to understand what are the contributing factors and how do they scale over time, and what can we expect in the future. And then, how do we reason about sustainable computer design in light of inherent data uncertainty? As I will be mentioning, there's massive uncertainty and unknowns, and so how do we even start doing a good job building more sustainable computer systems? And then how do we design more sustainable or less unsustainable computer systems, if you want? So let's start with the challenges. And I think there's multiple. And the first one is that sustainability really is a multifaceted problem. Yeah, it's much more than just global warming. Obviously, global warming is really important. It's really here, but there's more to it. Yeah. So as we all know, greenhouse gas emissions lead to global warming. Earlier this week was in the news in Los Angeles, Southern California, there's bushfires because of extreme drought for a number of months. Bushfires, drought, hurricanes, flooding, and so forth. Unfortunately, it's in the news every couple of weeks. Now, you may wonder, what is the contribution of ICT to global warming? Well, it turns out from a relatively recent study that ICT is responsible for about 2 to 4% of global greenhouse gas emissions. You may wonder, well, 2 to 4%, should we really worry about? Well, the thing is, it's increasing, for one, and to put it into perspective, it turns out to be on par with the aviation industry. So it's not a small contribution. And it is something we should worry about, right? The United Nations just recently reported that without urgent action, we would end up with a 3 centigrade global warming increase, and definitely not meet the 1.5 Paris Agreement target that we set out a couple of years ago. So clearly, something needs to be done. But sustainability is more than just, quote unquote, combating global warming. It's a much broader problem, actually. It's also about the raw materials that we need to manufacture the computing devices that we use on a daily basis. And there's lots of materials that we need to use. For example, the World Bank has projected that we need 10 times more metals by 2050 under a 2 centigrade scenario. The EU has done similar analyses reporting that we would need 60 times more lithium by 2050, 15 times more cobalt by 2050, and 10 times more rare earth materials by 2050. So there is transitioning from a brown electricity industry to a more green electricity industry clearly requires much more materials, and something that is sometimes underlooked at, right? Now, you may wonder, what kind of materials do we need to manufacture the IC devices that we are using on a daily basis? Well, in the 1980s, it's probably okay to have, we needed like a dozen materials or so. In the 1990s, we needed a couple more, but in the years 2000, things started to explode because of the end of the large scaling. We had to go through instead of having 2D transistors, we had to go through to 3D transistors, which are much more complicated to manufacture, and as a result, we need many more materials. So as you can see, this is Mendeleev's table, as you all know, and we need pretty much all elements to manufacture the integrated circuits that we are using on a daily basis. Now, the thing is, some of these materials are rare, and luckily, some materials are really abundant, like oxygen. So the y-axis is showing the availability on the Earth crust on a logarithmic scale. Oxygen is at the top, luckily for us. And silicon is there too, which is also a key element for semiconductor manufacturing. But there's many materials that are much rarer on Earth. For example, at the bottom right, you can see gold, platinum, and so forth, other materials that we need to manufacture integrated circuits. Now, extracting some of these materials is a very energy-intensive industry, and it's also a very carbon-intensive industry. So this graph is showing the amount of energy and the amount of CO2 emitted in the process of extracting raw materials. And for example, for copper, to extract 1 kilogram of copper, we are emitting about 4 kilograms of CO2 in the atmosphere. It's not a great trade-off, but it's not as bad as for gold, for example. To extract 1 kilogram of gold, we are emitting about 15 tons of CO2. That's something we don't really realize, but it's clearly a very carbon-intensive industry. In addition to availability of materials, there's also a supply chain risk. And we've become aware of this as we went through the COVID crisis. So this graph is showing the HHI index. It's basically quantifying to what extent the material is coming from a single country. And so the higher the index, the higher the monopolism for that particular material. And some of the rare earth materials have a very high index, meaning that there's only a single country in the world that is providing these rare earth materials. And China, for example, is a country up there. Yeah. Supply chain risk is a real risk when it comes to materials. So we have global warming, we have raw materials. Another side effect of how our business is being run is the huge amounts of e-waste. Yeah? Because we have a linear economy, right? So we buy stuff, we use it for a number of times, and then we throw it away. Yeah? This graph is showing the amount of e-waste that we are producing as a function of time. And today, we're consuming about, or we're producing about 8 kilograms of e-waste per capita per year. Yeah. So this includes both small and large appliances, so that this is not just smartphones that we are no longer using, it's also fridges, everything that has an electronics component to it. Now, the sad news is that worldwide, only 17% gets recycled. Yeah. In Europe, the percentage is higher. It's around 40%. It's not great, but it's definitely higher. But worldwide, it's only 17%. So it's something to worry about, right? And many of those, much of this e-waste ends up in landfills in Ghana, for example, in Western Africa. So it's a big concern. Also, in the process of manufacturing the IC devices, we need a huge amount of water. So TSMC is, I will be showing a graph up next, showing the amount of water that is needed for semiconductor manufacturing. This graph is showing, this is a graph showing, coming from IMEC, which is a semiconductor research institute in Belgium. And they collaborate with all sorts of companies worldwide in the semiconductor industry. And they recently started a program to investigate the sustainability impact of semiconductor manufacturing. And one of the results that they have here is the amount of ultra-pure water that we need per square centimeter of semiconductor integrated circuit for different tech nodes, from 28 nanometer all the way down to 3 nanometer. Yeah. So as you can see, there's a clear increase over time in terms of the amount of ultra-pure water that we need to clean the wafers in the manufacturing process. What is the what? The ITRS target. Oh, that was a projection that ITRS made at some point, but clearly industry is deviating from this target over time. So they expected it to go down, but in reality it went up. That's my conclusion, yes. So here is a graph showing the total amount of water that TSMC is using on an annual basis. Yeah. So around this time, it's about 100 million metric tons of water that they are using per year. It's a very abstract number, and I did the calculation last night, and it's about 100 Olympic swimming pools per day. 100 Olympic swimming pools per day of water that they need in a manufacturing process. Yeah. So it's a huge amount of water, and Taiwan is an island, and they have to share the water with the farmers. Yeah? And if there's drought, then this sometimes leads to social tension. The industry needs water, but the farmers also need the water. So it's a real problem affecting daily life of many people. Yeah? And also, when we want to solve the sustainability problem, or at least reduce the environmental footprint of ICT, I think we also need to come up with new business models and better legislation. I'm sure we can design computer systems that are more sustainable, but this is not going to be a sufficient condition. It's going to be a necessary condition, but not a sufficient condition. I think we also need to change the business models such that we rely less on raw materials, we have less impact on climate, the reduced amount of e-waste, and so forth. So we as computer scientists, I'm really convinced that we need to reach out to people, to business people, to legislation people, to come up with the right environment for us to move to a different business models and a different mindset when it comes to the environmental footprint of computing. So I hope I've convinced you that sustainability is much more than global warming. But there's other aspects that make it challenging to do research in this area, especially there is inherent data uncertainty. And there's many unknowns, and there's lots of industry secrecy. So for example, if we look at this LCA, so LCA stands for a life cycle assessment from Apple iPhone, they're literally stating that for some parts of the carbon footprint, they have to rely on some estimations, some assumptions, industry-wide assumptions, so they can't really provide explicit numbers for their specific supply chain. So that's related to the manufacturing of the devices. When it comes to the operational side, estimating how much energy and how much carbon a particular device is going to consume over the lifetime during the usage, there's even more uncertainty, I would say. So Apple is assuming a 3 to 4 year period by the first owner of the device, and then they use historical data to make predictions. Now, lots of uncertainty, but how predictive is historical data? We all know we are more and more attached to the computing devices that we are using. The number of apps is exploding. We're using it all the time. And we all know that these type of devices are really addictive. And if you have children, I have 4 teenagers in the household, I know how addictive these type of devices can be. So using like historical data to make projections is probably the best we can do, but we have to be a little careful. So lots of data uncertainty. And then the last thing that makes it challenging is that we need to account for the entire life cycle. It's not just about the usage part of the computing device that is affecting the total carbon footprint. We have to look at the entire life of a computing device. So if you think about the life of a computing device, we're going from material extraction to manufacturing to assembly, product use eventually. That's what we as users are confronted with. Hope maybe some repair maintenance is happening, and then eventually we are dismantling and we are hopefully recycling or reusing parts of the devices that we have been manufacturing. So the first part is typically called the upstream embodied footprint. The middle part, product use, is typically called operational footprint, and then at the end we have downstream embodied footprint. Anna made a case for sustainable computing in the cloud. She was mostly focusing on the operational footprint. I would say we also need to account for the embodied footprint because it's important, as I will point out later as well. So power efficient or energy efficient computing basically ignores the embodied footprint, and if you want to reduce the total environmental footprint of computing, you have to consider both the operational side and the embodied side of it. To make things even more complicated, if we make our devices more carbon friendly or more power or energy efficient, is this going to lead to an overall reduction in carbon footprint? Unfortunately not. Like I said, it's a necessary condition, but not a sufficient condition. And the reason is really this Jevons paradox. You may have heard about this before. If you make a device or a particular system more efficient, then there could be a rebound effect where this device is being deployed more or is being used more. And as a result, you end up with a net increase in the total carbon footprint. So this paradox is named after Jevons, who was an economist, and he observed that when James Watt came up with a more efficient coal-fired steam engine, that the total consumption of coal actually went up instead of going down. And the reason was that because the devices became more efficient, more companies could afford having a steam engine, and as a result, more steam engines were deployed, and as a result, more coal was being consumed. And this is very much true for the computing industry as well. If you make your server more power efficient, then the immediate reaction from the data center infrastructure operators will be, oh, great, and we can host more servers within our power budget, because many of these data centers are really bound by the total amount of power that they have available. They have this 8 megawatt, 10 megawatt, whatever power budget that they have, and then if they can stick in as many servers as possible within that power budget, they will do so. Okay, so hopefully I've convinced you now what the challenges are. So what are the contributing factors when it comes to computing? Yeah? And the first time I thought about this when I was teaching this course on sustainable computing at Ghent University. I came across this Kaya identity, and I thought about ways to use this very simple but very insightful identity to reason about what the impact is of computing. So the Kaya identity quantifies what is the global CO2 emissions of humankind and breaks it up into different factors. It's the multiplication of the population, the amount of GDP per capita, the amount of energy needed per unit of GDP, and then the carbon intensity for generating that energy. Now, if we look at the different numbers, we end up with this plot. And so population is growing. GDP per capita is also growing, which is great, right? We're generating more welfare across the globe, which is a good thing. And then energy intensity, the amount of energy that we need to produce 1 unit of GDP is going down. So that's good. I mean, it's a result of industry being more energy friendly. It's because we are moving away from a making industry to a service industry. So in a sense, that's a good thing. And then carbon intensity, the amount of CO2 that we are emitting in the atmosphere per unit of energy that we're consuming, is also going down. It's going down slowly, but it's going down, which is a good thing. Yeah. But if you add up everything, we end up with an increase in CO2 emissions, and that's why we are where we are today with the global warming problem. Yeah. So the question I asked myself: can we sort of reformulate this Kaya identity for us, computer architects, computer scientists, to reason about? And I've come up with a breakup of this Kaya identity, and I made a distinction between embodied emissions and operational emissions because we want to account for the whole life cycle of a computing device. And then this GAG protocol has this notion of scopes. It's a little bit confusing, but from a manufacturing standpoint, and so to produce the chips that we use in our devices, Scope 1 means the chemicals and gases emitted in the process for cleaning the wafers and air conditioning in the facilities. Scope 2 is the carbon emissions as a result of the energy that we're consuming to manufacture the devices. Yeah? So in Taiwan, the energy is relatively brown compared to other places in the world. So that's contributing to Scope 2. And then Scope 3 is a result of the upstream materials that TSMC is bringing in to manufacture the integrated circuits that they eventually sell. Yeah. Because there's very little data about Scope 3, I'm not considering here, but based on what I mentioned before, it's pretty clear that the embodied footprint Scope 3 will be related to the size of the chips that we are manufacturing, or the number of chips that we are manufacturing. So in that sense, the equation for Scope 3 will be quite similar to Scope 1 and Scope 2, as I will be presenting in a minute, but I don't really have concrete data. And then the operational emissions is the total carbon emissions during the whole lifetime for product use. So I came up with these equations. So for the embodied Scope 2 and Scope 1, they are very similar. So we have the total number of chips that we are manufacturing times the number of wafers that we need to produce those chips, times, in terms of Scope 2, the amount of kilowatt hours that we consume to produce one wafer, and then multiplied by the carbon intensity, so the amount of CO2 emissions emitted per kilowatt hour that we are using. And Scope 1, number of chips times the number of wafers per chip times the carbon 2 equivalent because of the chemicals and gases to produce a wafer. And then on the operational sides, we have the total number of chips times the total energy that this chip is going to consume over its entire lifetime as a result of product use, times the carbon intensity at the product use side of the device. You know? So we have these different terms. How do they scale over time? Let's take a look at the different terms that we have here. So the number of chips appears in all three equations, and if you look up some numbers, so here I got some numbers showing that the total number of chips that we are producing worldwide is increasing by about 9% per year. Yeah, so it's an exponential growth curve. Since COVID, we know what exponential curves mean in practice. So 9% per year is a pretty steep increase, I would say. So how many wafers do we need to produce those chips? That's related to the size of the chips that we are producing. The larger the chips that we are producing, the more wafers that we need to produce all those chips. It turns out that especially for high-end systems, that die size is stagnating. And that's especially for high-end systems, we are reaching the reticle limit, which is around 800 square millimeter, which is what we can design a single chip in as a result of the manufacturing process. Yeah. So I think it's fair to assume that the number of wafers that we need to produce all those chips is not growing. Now, what about the total energy needed to produce a wafer? And so here I'm pulling up another graph from this study from IMEC showing what is the total amount of energy needed to produce one wafer in different tech nodes, from 28 nanometer at the bottom to 3 nanometer at the top. Yeah. And what we can see is that the total amount of energy needed to produce a wafer is also increasing by about 12% per year. Yeah. And that's because the chip manufacturing process becomes more and more complicated. There's more and more steps involved, as you can see in the plot. Yes?
What kind of chips are considered everything for consumer electronics?
Right. All chips for consumer electronics, yes. Yeah. Mm-hmm. Okay. And yeah, another study from Greenpeace, East Asia, and you might, if you're skeptical, you might say, well, Greenpeace, it's going to be a biased study, but if you go through it, it's actually very thorough. They are claiming that the semiconductor industry is going to double the amount of energy consumption, electricity consumption by 2030. Yeah. So it's a huge increase. So quite similar numbers in terms of the chemicals and gases needed to manufacture these integrated circuits. That's because of more complicated manufacturing process, so we need more chemicals and gases to clean the wafers and so forth. So this is increasing by about 9.4% per year, according to this IMEC data. And then there's also some good news, like the carbon intensity is decreasing worldwide. It's decreasing. In Europe, it's decreasing about 2.5%. In different parts of the world, you would see different numbers. TSMC also has made commitments about using more and more green energy, so that's definitely going to help Scope 2 embodied emissions. And when you look at data center deployments, and Gupta et al. In HPCA 2021 had a very comprehensive study showing for data center, for example, and then I'm referring to the operational side, carbon intensity for the operational side. That study is showing that for hyperscalers, the total carbon footprint is actually not increasing as steeply as the electricity increase. So electricity use is increasing very rapidly, but the carbon increase is not increasing as fast, and that's because of the use of green energy. And they generate their own green energy, or they use contracts with electricity providers. But there is a pitfall there in the sense that the green energy used by these hyperscalers cannot be used by other people in that region. Yeah. And in fact, in some countries in Europe, at least that I know, like in Ireland, for example, or in the Netherlands, there has been a ban on installing new data centers because they consume too much electricity, and they would take up too much of the green electricity that is available, so that the whole nation would no longer be able to hit their green electricity targets that they set forward. Yeah. So there is a little bit of greenwashing going on there, if you ask me. Yeah. And in terms of the operational energy consumption, I think computer architects and hardware designers have done a great job, and also software developers have done a great job reducing the operational footprint of computing devices. Things like DVFS and clock gating and power gating are all techniques that are widely deployed that actually help us to reduce the operational footprint of computing devices during product use. Yeah. So if we use these equations and the annual growth rate numbers and take a look at what it means for computing, then we end up with these two plots. So the plots on the left-hand side is showing the normalized emissions, assuming that initially the embodied footprint is responsible for about 80% of the total emissions. The plot on the right-hand side is assuming that the operational emissions is responsible for 80% of the total emissions. So it's mostly operational emissions dominated. And different types of devices have different relative weights of embodied versus operational emissions. I will be showing graphs about that later. But the important thing to note here is that, for one, total carbon footprint continues to increase in both scenarios because of the scaling factors that I just talked about. And second, the embodied emissions are growing rapidly, and they're also growing in importance and will dominate at some point in the future if they are not already dominating today. And the reason is really the increasing number of chips and the growing energy intensity in chip manufacturing. So if you put it all together, so the demand for chips is increasing. That's probably also a result of Jevons paradox. Yeah? GHG emissions, both Scope 1 and Scope 2, is increasing with new tech nodes. Transition to green energy is not moving fast enough. In Europe, 2.5% per year is not good enough to compensate for the 9% increase in the number of chips or the 12% increase in carbon emission or energy use per wafer. So it's not moving fast enough. And in addition, it does not affect Scope 1 and Scope 3. Right? So even if TSMC were to use 100% green energy, they still need the chemicals and the gases. They still need the raw materials. Yeah? So it's not a silver bullet solution to go to green energy. There's also other concerns that we have to worry about. And then embodied emissions dominate already today, or they will soon dominate in the future. So with these insights, how do we reason about computer system design and making it more sustainable in light of this inherent data uncertainty? And my answer is to embrace it. Let's do very simple modeling. I have background in computer architecture modeling, so this came as a natural next step for me. And I've been working and I've been proposing this focal, very simple first-order carbon model that allows us to reason about the environmental footprint in computer architecture design without having to rely on very precise data. Yeah? So it's a top-down parameterized model. It's deliberately simple, built upon first principles, as I will argue, and the goal really is to provide insight. Yeah? And the key idea is to use proxies for the embodied and the operational footprint because we want to account for the entire lifetime of a computing device. And because it's not always known ahead of time how important the embodied footprint will be compared to the operational footprint, we will parameterize that. And then by changing this parameter, we can consider different scenarios and see under what scenarios one design point would be more sustainable compared to another design point. And we will consider different use case scenarios to account for rebound effects to some extent. We can't include all kinds of rebound effects, but at least some rebound effects we can account for. And I would argue, in spite of its simplicity, we can do actually quite powerful analyses, because if we reach similar conclusions across a range of scenarios, then we can be quite certain that the conclusion is valid. Yeah. If for different scenarios we end up with different solutions, then we have to be a little more careful. Yeah. So, proxies. So what is a good proxy for the embodied footprint? As I mentioned before, the unit of production in a semiconductor fab is a wafer. Yeah? And so as a result, the bigger a chip that we are manufacturing, the bigger its environmental footprint is going to be. Yeah? This plot is showing a normalized embodied footprint per chip relative to a die size of 100 square millimeter, accounting for two effects. The first one is that a wafer is a circular structure, and the bigger we make our individual chips, the more area we will lose around the edges of the wafer. Yeah? So that's the blue curve. Yeah? So there we are assuming that every chip that we are manufacturing on the wafer is going to be a perfectly correct chip. So that's called perfect yield. Yeah? All the chips that we are producing are perfectly functioning as expected. Now, the manufacturing process is not perfect. There is something called like defect deficiency. And TSMC, and for their volume production, has reported 0.09 defect density per square centimeter. And if we use this as an input to the Murphy model, which people have been proposing and using, then you end up with this red curve showing what is the normalized embodied footprint as a function of die size. Yeah. So the bigger the chip, the higher the yield problems that occur. Yeah. So a proxy that I've been advocating for is chip area. If we include yield, then you may want to refine this equation or this proxy and make it a function that approaches the red curve rather than the blue curve. But I decided not to do that because the semiconductor industry and the processor manufacturers also binning processors. So even if a multi-core, for example, a multi-core processor or a GPU with hundreds of SMs, or a multi-core processor with 24 cores, for example, if it turns out that one of the cores or a couple of the cores or a couple of the SMs are not properly functioning, those companies, they can still sell those devices with a smaller core count. And that's effectively what they're doing. And it's a process called binning. Yeah. So even though the red curve would be very pessimistic, I think in reality we are closer to the blue curve. But still, there's some lost. There are some losses because of yield. Yeah. So the embodied footprint proxy is chip area, and to make it more concrete, so if you have chip area in square centimeter, if we multiply this with the carbon, with the energy consumption to produce one squared centimeter, and then produce with the carbon intensity at the manufacturing site, so then that's how we can see that this actually makes sense, right? And so this plot on the right is showing the total amount of energy needed to produce 1 square centimeter for different technology nodes. So chip area is the proxy for the embodied footprint, and that's something that we as computer architects can reason about. Yeah? When it comes to the operational footprint, I've been considering 2 different scenarios. The first one is a fixed work scenario, and intuitively that's the most common scenario people would have a mental map for. And so we assume that the amount of work that a device needs to do is fixed. Yeah? So then the operational footprint is going to be proportional to the energy consumption. Yeah? So in this plot, I'm showing power consumption as a function of time. So it's the total amount of energy that is being consumed that is going to determine what is the operational footprint for executing that job. Yeah? Okay. But if you have a more efficient design, if you come up with a more efficient processor, then this processor can do more work. And that's effectively what we see. It's a sort of a result of a rebound effect, a result of Jevons paradox. And what if we just assume that we will take on more work, but use the device for the same amount of time? And this is what I call a fixed time scenario. At that point, the total operational footprint will be proportional to power consumption. So the total area of the orange, of the yellow and the orange area will be proportional to power consumption. So in this fixed time scenario, power consumption would be a proxy for the operational footprint. And it's accounting for some sort of a rebound effect. Okay, so now we have a proxy for the embodied footprint, a proxy for the operational footprint, how to weigh those two. And that's very much dependent on a different type of different factors. And the first one is the device type. And this is a graph I took from Gupta et al. At HPCA 2021. I definitely recommend you reading this paper. It's very insightful. And they have been, based on LCAs from different types of devices, they have been reporting what is the contribution of the embodied footprint versus the operational footprint. And so the embodied footprint here is attributed to production, and then the operational footprint is attributed to use. So battery-operated devices like smartwatches, smartphones, tablets, even laptops are mostly dominated by the embodied footprint, whereas always-on devices like high-end desktop computers, gaming consoles are more dominated by the operational footprint, which sort of makes intuitive sense.
Why are there different numbers of buyers here? Was that just sort of different? So 2 buyers, 2 buyers, 1 buyer, 3 buyers?
Those were different types of smartphones, if I recall. So this would be this was probably smartwatches, and then one smartwatch, and then another one, and then 2 smartphones, one smartphone from, say, Apple, and another one from Google or something like that. I would need to look into the original paper to get that. It also depends on the lifetime of a device. Obviously, if we extend the lifetime of a device, then the relative contribution of the embodied footprint will go down. I had a discussion earlier with Anna. Extending the lifetime of servers would decrease the relative contribution of the embodied footprint compared to the total footprint. So this relative weight also depends on lifetime, and obviously the energy mix. If you're using a device in a country, say Norway, where you have lots of green energy, the relative weighting of embodied versus operational footprint will be very different if this device is being used in Norway compared to, say, India, where we have much more brown energy. So because these things are a moving target, things are changing as we speak, so let's parameterize and see where we get. So this focal model, very simple model, computes what I call the normalized carbon footprint, NCF. So it's making a relative weight of the proxy for embodied footprint. So it's weighing the relative chip area of design X versus design Y, and also relatively weighing the proxies for the operational footprint, energy or power. And then the alpha parameter is really a function of the device type that is being used, the lifetime of the device, the rebound effect, and so forth. So as I promised, just some concrete examples of what these alpha values would look like. I've been picking different types of devices. On the left-hand side, we have an Apple smartwatch, we have an iPhone, a Mac Mini, a MacBook Air, another MacBook, and then a couple of desktop computers, and a gaming console. And so this alpha value varies widely. So for mobile devices, They are mostly dominated by the embodied footprint, so the alpha value will be typically fairly high, whereas compared to medium-range desktops, it would be around 50%. And then for high-end desktop and gaming consoles that are always powered on, the alpha value would be around 0.2. Yeah. So we have this very simple model, but can we gain some insight from this very simple model? And surprisingly enough, I think you can get a lot of insight from it. So I've been using this model to sort of reassess some of the archetypal design decisions that we typically make as computer architects. As a computer architect, we think about things like branch prediction and speculation. We think about caching, multi-core, heterogeneity, DVFS. How does that affect sustainability? And I used existing results from the literature to make an assessment of how sustainable particular processor design choices are. And I've been classifying these archetypal processor design choices into 3 big classes. The first one is strongly sustainable. So if I classify a design choice as being strongly sustainable if it reduces the carbon footprint under both the fixed work and the fixed time scenario. And so even if under a rebound effect, we end up with a reduced carbon footprint, then I would claim this is strongly sustainable. On the other hand, if the carbon footprint only reduces assuming a fixed work scenario, but not the fixed time scenario, then there is a risk for a rebound effect. There is a risk that our optimization is going to lead to a net carbon increase rather than a carbon decrease. Yeah? So some archetypal process design choices end up there, and then some design choices are less sustainable as they increase the carbon footprint under both the fixed work and the fixed time scenarios. And I've been using analytical models and previously published results. This is all available in the ASPLOS 2024 paper. So this was probably the lowest carbon project ever, just using existing results and analytical modeling. Yeah. So some interesting conclusions. So I'm going to go through a couple of these examples. I highlighted them in green, bold text for each of those cases. So like a die shrink, it's a common technique. You may have heard about this Intel tick-tock trade-off of optimizing the microarchitecture in a given chip technology node, and in the next iteration, they would go to the next tech node with the same microarchitecture, and then they change the microarchitecture again. So this is tick-tock. So a die shrink means we have a given microarchitecture in a given chip technology node. We re-implement the same microarchitecture in the next generation technology node. Yeah. So the question is this strongly sustainable, weakly sustainable, or not sustainable? Well, when it comes to the embodied emissions, I would argue it's a net. It leads to a net decrease. Yeah. Ideally, with going from one technology node to the next technology node, your chip area would reduce by a factor of 2. Yeah. So 50% less chip area is required because the transistors become twice as small, ideally. But energy consumption for manufacturing is going up between 2 technology nodes by about 25%. So that's the annual growth rate was around 12%. If we assume a new generation takes about 2 years, today it's taking more than 2 years. But if we assume it takes about 2 years, then that's an increase by 25%. And chemicals and gases is around 20%, going from one tech node to the next tech node. So chip area decreases by 50%, but manufacturing, the chip area increases by about 20%, so we end up with a net decrease. So the embodied footprint, as a result of die shrink, would actually lead to a net reduction in embodied emissions. For the operational emissions, depending on whether we assume classical scaling or post-Denard scaling, today we are in a post-Denard scaling era where we are power constrained. So Under a fixed work scenario, yes, operational emissions would go down. Under a fixed time scenario, they would not go down. So it would be neutral. So overall, I would argue that a die shrink actually leads to a net reduction in environmental footprint. But this is not what we've seen in the industry. Yeah? And that I would say is an example of Jevons paradox. Yeah? So yes, the carbon footprint for manufacturing a transistor in a new technology node becomes less and less carbon intensive. But because the transistors have become less and less expensive, we've been deploying more and more transistors. Yeah, chip area has remained the same. So we have been deploying twice as many transistors as we go from one tech node to the next. So as a result, we end up with a net increase in carbon emissions. Yeah? So in contrary to what we would have achieved with simple die shrinks. Yeah. Multi-core is another interesting example. It's a little bit complicated to understand, but let me try to explain. So here I'm showing NCF, normalized carbon footprint, as a function of performance for the fixed work and the fixed time scenarios, as a function of chip area. Yeah. So I've been relying on the Hill and Marty paper, which is about extending Amdahl's law for multi-core, and they use this notion of a base core equivalent, which is basically a unit of chip area. And I've been exploring different chip sizes, and we have 1 BCE 2, 4, 8, 16, and 32. And if we were to use the entire chip area to build a single core processor, we would achieve the NCF shown and the performance shown by the black line. Yeah. If you compare that to multi-core, we end up with these colored curves, depending on the amount of parallelism in the workload. Yeah. And so the higher the degree of parallelism, ranging from 0.5 to 0.95, we see that the curves are moving towards the bottom right on these plots. Yeah. So the first insight is that multi-core is strongly sustainable compared to single core. Yeah. If we compare this design point here, 32 BCEs single core versus 32 BCEs used for multi-core, we end up with higher performance and reduced carbon footprint. Yeah? Both under the fixed work and in the fixed time scenario. Yeah? When you compare these two design points here, we also see a reduction in carbon footprint. So compared to, this was definitely not the intention of the industry. Yeah? They went multi-core because they had to, because of post-and-art scaling, but as a nice benefit compared to single-core processors, it also reduces the environmental footprint. Parallelizing software is weakly sustainable. Yeah. If we compare these design points, so say we have software that is parallelizable for about 50%. 50% of the code can be parallelized, and we compare that to 95% of the code can be parallelized right here, then we see a reduction in carbon footprint and obviously an increase in performance as well under a fixed work scenario. But under a fixed time scenario, we actually see an increase in carbon footprint. Yeah. Because the device becomes more efficient, because software is more parallel, we will start doing more work, and as a result, we will end up with a higher total carbon footprint because of this rebound effect. And then a third conclusion, which is quite interesting, I think, is that parallelizing software is more sustainable than adding more cores. So if you compare this design point here, for example, with 32 BCEs, so 32 cores, versus this design point with 16 cores. So here, software has been parallelized for now 90%, whereas here, software has been parallelized for 95%. So what we see here is that if you compare these two design points, this one versus this one, if we parallelize software, if we are able to parallelize 95% of the application versus 90% of the application, oh, I'm sorry, we actually see, and instead of keeping up with the 32 cores that we had, we are sober, and we go for 16 cores instead, then we can reduce the carbon footprint and at the same time improve performance, right? So there's a role for software people to play here. If we can somehow parallelize software more than we do today, I know it's hard, but that is a more sustainable way than adding more cores and leaving software as it is. Yes? No, it would be strongly sustainable because it occurs for both the fixed work scenario right here and the fixed time scenario right here. It's
I'm missing the intuition for that. I feel like you're utilizing things more, which is great, but doesn't that just mean overall you can get more done? Okay, so you can get more done on your machine in the same amount of time.
Yes, but this design point also has fewer cores. So if it does more work, then it will consume less energy than if we were to go to the 32-core alternative.
Okay. I guess maybe what I'm thinking is, in practice, people just do both.
Yes, industry would definitely go from 16 cores to 32 cores and also parallelize software. So that's why I'm saying, and I have a slide later coming up, we have to be a little more sober as we move to new technology nodes. And so if we don't use all the transistors that we have, but only a small fraction of it, or a fraction of it, and so be a little bit more sober, we can at the same time improve performance and also reduce total carbon footprint. That's essentially what this boils down to. An example of a weakly sustainable technique is speculation. Like branch prediction is widely used and very heavily relied on in high-end processors. Branch predictors consume power. They also lead to higher power consumption because there's more activity in the core. But if the increase in power consumption is less than the improvement in performance, we end up with a net energy reduction. And that's actually what we see based on experiments. Yeah. So speculation in general would be weakly sustainable. Yes, if the amount of work that needs to be done is fixed, then we see a reduction in energy consumption, but an increase in power consumption, and therefore it's weakly sustainable. Another example is acceleration. So here I've been taking data from an interesting paper out of Stanford, published in Eeckhout 2010. So in this paper, they were comparing an H.264 accelerator against a general-purpose CPU implementation of the same algorithm, and they would both achieve the same performance. Yeah? And no surprise, the accelerator is much more efficient. It requires much less chip area, 15x less chip area, and it consumes 500 times less energy to get the same amount of work done in the same amount of time. Yeah? So the question then is adding this accelerator on top of the CPU, is that going to be sustainable or not? Yeah? So in terms of the embodied footprint, we need to add the accelerator next to the CPU. So that's going to add a 6.5% increase in chip area. Yeah. So the embodied footprint is going to increase. But in terms of the operational footprint, we may actually reduce the operational footprint. Yeah? If we use the accelerator, it's going to be way more efficient than using the CPU to get the work done. So depending on how often we use the accelerator, we may end up with a different total carbon footprint. And I've considered two scenarios where the embodied emissions are dominating, alpha equals 0.8 and operational footprint dominating alpha equals 0.2. So depending on the fraction of time that we spend on the accelerator will actually be sustainable or not. You know. And then with dark silicon, I would argue it's not going to be sustainable at all. So in the previous example, you know, we're assuming just a single accelerator, which takes about 6% of the chip area compared to a CPU. Today, you would see the inverse. If you look at an SoC, you would see half the chip, 2/3 of the chip devoted to accelerators. And the accelerators are only used when really needed. Yeah? So we incur the embodied footprint. So the embodied footprint would dramatically increase. The operational footprint would obviously be much less. But the question is, does dark silicon lead to an increase or a decrease in total carbon emissions? And I would argue, my conclusion at least, is that dark silicon is harmful when it comes to sustainability. Yeah. You know, you're adding so much chip area that you're not using most of the time. You can't use it most of the time because of power constraints. And so based on the exact same assumptions from the last slide, if we assume that the accelerators take up 2/3 of the total chip area, if the embodied emissions are dominating, the total carbon emissions would be way higher compared to no dark silicon. And if the operational emissions would dominate, we would need to use the accelerators for more than half the time, which is completely impossible in the area of dark silicon. So how do we design more sustainable or less unsustainable computer systems? Yeah. I'm not a doom thinker. It may seem like we're doing the wrong thing, or we've been doing the wrong thing for many decades, but maybe there's a possibility to design more sustainable computer systems. And I'm going to highlight a couple things what we could possibly do. So one case study, which I also included in the ASPLOS 2024 paper, was the following. Say we have and that goes back to your question. So if you have a multi-core in one generation with 4 cores, and the question is, what are we going to do in the next generation? Do we go in the next generation of tech node? We have twice as many transistors. So do we go for 8 cores? Or are we going to be a little bit more sober? You know, or are we going to go for 5 cores or 6 cores? You know? So that's really the design question here. And so the comparison point is the 4-core system in the current tech node. And the question is, what is going to be the carbon footprint if we go to a new tech node? First, when the embodied emissions are dominating on the left-hand side and when the operational emissions are dominating on the right-hand side, again, for a fixed work and a fixed time scenario. And it turns out that if we go all the way, as industry is doing, using all the transistors that we can, and go to 8 cores, then carbon emissions are going to increase under both the fixed work and the fixed time scenario. When the embodied emissions are dominating, and when the operational emissions are dominating, it's going to be weakly sustainable. Yeah? And when the embodied emissions are dominating, it's going to be not sustainable. But a sustainable path forward is, instead of going for 8 cores, we could go for 5 or 6 cores. In that case, we end up somewhere here, right? We still get a significant performance benefit and a reduction in total carbon footprint under both scenarios, both when the embodied emissions are dominating and when the operational emissions are dominating. Yeah? So despite this is a very simple model, and we come up with these conclusions across different scenarios, then I would argue, well, if we are a little bit more sober and use the resources that we have in a more sober way to design more sustainable systems, that's actually a pathway forward for the industry to go. Clearly, this is not what the industry is doing at this point. Hopefully, they may want to change that. Okay. Another case study. I have two more case studies. I'm not sure I will be able to cover all of them, but let's see how far we can get. So let me first start with this one. So in hardware design, there is this notion of PPA analysis. So power, performance, chip area analysis. So the PPA abbreviates these three aspects. And hardware designers in the Eeckhout community are very familiar with this type of analysis. And the idea here is, can we leverage this type of analysis to do a sustainability assessment? And we've been taking a traditional computer architecture design problem, which is to come up with instruction selection logic. And for those of you not so familiar with computer architectures, you basically have two extremes in core microarchitecture, CPU core microarchitectures. On the one hand side, you have out-of-order cores, high performance, but also very complex and very high power consuming, versus in-order cores, much lower complexity, but also much less performance. Yeah, ideally, you want to have something that approaches the out-of-order core in terms of performance and the complexity of an in-order core. Yeah. And prior to this sustainability work, I've been working in this space alongside with Trevor Carson, for example. We came up with the first architecture right there, the load slice core, LSC. And then there's been a couple others from other groups as well. Freeway from Uppsala. Forward slice core was a second generation of load slice core, which I developed with one of my PhD students. Casino is from a group in Korea, and then delay and bypass also coming out of Uppsala in Sweden. So different groups have come up with different core microarchitectures motivated by performance and complexity, but never was there the question, are these microarchitectures sustainable? Yeah. So I'm not going to go into too much detail into each of these architectures, so I'm going to skip these slides in the interest of time. But what we basically did was that we synthesized each of these architectures to a FinFET standard cell technology node to get an estimate of chip area, to get an estimate of power consumption. We also synthesized these designs to the chipyard fire sim infrastructure to obtain cycle accurate performance numbers. And then with the performance numbers, with the power numbers, with the chip area numbers, we can actually, and if we combine that with the focal model, we can actually make an assessment of what the sustainability impact is going to be of these instruction selection policies. And what we end up with is something like this, where we have NCF, the normalized carbon footprint on the y-axis, as a function of performance. I'm cutting it off here at 0.86%. What is interesting here, so everything is normalized to this out-of-order core, right? So ideally, you want to be at the bottom right here in this plot, high performance but low carbon footprint. What we could find out was this FSC and Casino and out-of-order, they are basically Pareto optimal points. Yeah? You can't do any better. LSC, freeway, and delay and bypass are not Pareto optimal. They are overruled by some of the other architectures here in terms of both carbon footprint and higher performance. And we came up with a couple enhancements to the FSC to obtain even better trade-off points, like FSC++ would achieve very close to out-of-order performance with an almost 40% reduction in carbon footprint based on this carbon model. Yeah. So this is something we published a couple months ago at Eeckhout. And then the last case study is work that I've actually done jointly with people from NUS, Tulika, and then I also see Pranav in the audience, about hardware reconfigurability. Yeah. So today, we are in this golden era of computer architecture where we're using accelerators to accelerate almost everything. Yeah? And surprising or not, if we look at the total number of DSAs, so DSA stands for the domain-specific accelerators that we have on the chip today, we have actually multiple tens of those on a chip. And this is true for both mobile type of servers as well as laptop and server processors. Yeah. And if you think about it, dark silicon is really trading off a chip area for power efficiency. Yeah. So clearly, this has an impact on the environmental impact. Yeah. And I would say, like, the dirty secret of dark silicon is the embodied carbon footprint. Yeah. So this plot is showing, again, based on data from IMEC, some normalized metrics per standard cell. So the red curve is showing the embodied footprint per standard cell. Yeah. And the blue curve is showing the chip area per standard cell as we go to new technology nodes. And both are exponentially decreasing, which is great, right? But as you can see, there is a difference in the slope. And the difference in slope implies that the embodied footprint per unit of chip area is actually increasing. Yeah? So the dirty secret of silicon really is the embodied footprint. And so the question we asked ourselves was, well, won't reconfigurable hardware be a solution here? And the vision was quite simple. So if we were to replace this sea of DSAs, these 30, 40 DSAs with a reconfigurable fabric that we can dynamically reconfigure for the different types of applications that we run, we may end up with a more sustainable system design. You know? And why would it be more sustainable? Well, the embodied footprint would be less. So if you compare the chip area of reconfigurable fabric compared to tens of accelerators, then this reconfigurable fabric might be smaller than the sea of DSAs. So that would be a win. On the flip side, the operational footprint would be higher when using reconfigurable fabric compared to the DSAs, because the reconfigurable fabric will be less efficient than the DSAs, and there will be some runtime overhead. And so the question is, where exactly is this trade-off point? Is it such that there is a point where we can, is there such a thing as reconfigurable hardware being a more sustainable alternative to a sea of DSAs? And it turned out that indeed that's the case. I see that we're running out of time here, but we did some simple analysis building upon the focal model that I talked about. And basically what we came up with was this notion of a critical DSA count. Yeah. And it basically says that if the total number of accelerators that you want to integrate on a chip, if that is larger than the CDC, the critical DSA count, then a reconfigurable fabric will be more sustainable compared to the C of DSAs. And if you plot this CDC as a function of this ratio alpha, then we see that this is monotonically decreasing with alpha. Yeah. No surprise, I would say. Yeah. As the embodied emissions are dominating, the CDC will decrease, meaning that replacing fewer DSAs with a reconfigurable fabric will be more sustainable. Yeah. What we also note is that the curves are more sensitive to A than to E. I didn't explain A and E, but A essentially is the chip area of a DSA relative to reconfigurable fabric. And E similarly is the relative energy consumption of the DSA compared to the reconfigurable fabric. So it turns out that it's more sensitive to A than to E, and that's to say that the implication of this is that if you want to make your DSAs more sustainable, you should focus on area efficiency rather than energy efficiency. And that's probably contrary to what people are typically doing. When they report results for accelerators, they are mostly focusing on to what extent this accelerator is more energy efficient compared to alternatives. It's not really quantifying as much what is the area efficiency, which is, according to this result, is more important when it comes to sustainability, especially when the device is mostly dominated by the embodied footprint, as you may guess. Then another issue is concurrency. It's not such that one application would just use one accelerator. Some applications use multiple accelerators, and you could have data flowing from one accelerator to the next. So reconfigurable fabric would need to be big enough to accommodate multiple accelerators for concurrency. So that is obviously shifting the curves upwards. But the good news is, according to many different studies, or at least several different studies, that the degree of concurrency in many applications is relatively limited to 3, 4 concurrently used accelerators. So the bottom line is that, and again, under different scenarios, if we can replace, for example, if the embodied footprint is dominating, then if we can replace 4 to 12 DSAs with a reconfigurable fabric, then we would end up with a more sustainable design. And even when we are operationally dominated, replacing 8 to 25 DSAs would still be more sustainable compared to having around 40 DSAs as we see them today. Okay, so then Pranav did an excellent exercise to actually figure out what are the actual numbers for A and E that I used in the models. And the overall conclusion, I'm skipping the results here. The overall conclusion is that for practical designs, CGRA, so CGRAs is a particular fabric for reconfigurable computing. It stands for coarse-grained reconfigurable array. Then if we replace a handful of DSAs with the CGRA, we can actually reduce the carbon footprint up to a factor of 7 in the most optimistic scenario. In the most pessimistic scenario, we would still decrease the carbon footprint by about 60%. So that brings me to the end of this talk. So I hope I convinced you that the contribution of ICT to global warming is significant and it's rising. And doing research in this space is challenging for a number of aspects, but still I think we can use first-order approximations to make sensible design decisions. And if you want to read more, here are some pointers. You can find it on my website as well, in case you're interested learning more about this topic. Thank you. I missed the first part of your question.
You claim that for reconfigurable hardware is more efficient, but would it take more area or the same area to implement the same kind of logic?
Well, if you compare one specific DSA implementation versus a CGRA would consume much more chip area than one DSA. But the point is that to support many different applications, you need multiple DSAs. So the total chip area for all those DSAs would be larger than this one reconfigurable array that you can reconfigure on the fly as new applications come in. And so this chip area of the CGRA would be much smaller than the sum of all the DSAs that you would have. That's where the benefit is coming from.
That makes sense.
Yeah.
the impact on the body, CO2. So, yeah, maybe I missed it, but like, do the models take into account like, yeah, robustness or like design to try to make lifetimes longer for chips?
Yeah, lifetime is definitely an important aspect of it. It's not explicitly mentioned in the model, but if we were to anticipate what the impact is going to be of extending lifetime, then that would change the alpha value from a higher value to a lower value, because then the emphasis would be much more on the operational side compared to the embodied side. Right.
So that might be a reasonable proxy for that. But then the architectures you're coming up with may be more error prone in terms of like their half-life going down potentially, right? If you're not directly trying to.
That's right.
I'm not an architect, I don't understand. Like, we have good models for like how density impacts the failure rate.
Yeah, that's a good point too. Yeah. So fault tolerance also comes into the picture here. And it's definitely true that today's designs already have spare units implemented to overcome specific errors that may happen over the lifetime of the devices. So the electronic devices degrade over time, but if you have a spare part, then if you have some logic to figure out that some component was broken, then you can replace it with something else. That's an interesting sustainability question by itself, because if you need to provide or provision spare parts, then that adds to your embodied footprint. It also adds a little bit to the operational footprint, because from time to time you need to check whether parts are still properly functioning or not. That's going to be a minor part for sure. But then what you will gain is longer lifetime. So is the gain in lifetime going to compensate for the increase in embodied footprint? I don't know. It's an interesting research question, yes.
It kind of goes against the linear economy, right?
Yeah, sure.
The point of linear economy is to sell more devices.
Exactly, yeah, and that's...
You're not paying for the embodied cost. Okay, you're pushing it away somehow.
Right. Yeah, I would argue, yeah, we're not paying as humankind, we're not paying for the real environmental cost of all the things we're doing. At some point we will pay. If we have more and more hurricanes and more bushfires and so forth, we will pay. But for now, we're not paying. I agree. Yes.
Thanks. Very, very interesting. Regarding this is maybe related to the previous but one question about the domain-specific accelerators and replacing them with FPGAs. I guess what I was thinking was, if you had several applications that are going to be running concurrently, and collectively they're going to be using maybe a large proportion of the 40 or so DSAs you would have had, is that feasible? Can you, like, I don't know how quick these things can be reconfigured. Presumably you can't reconfigure every context switch or anything like that.
Yeah, there's definitely a cost associated with reconfiguring reconfigurable logic, CGRAs or FPGAs. Yeah. But it turns out from several studies that it's not like we're using tens of accelerators at the same time. It would also be impossible to do so because of dark silicon. So what you typically see in applications is like 2, 3, maybe 4 DSAs are being used at the same time. So if you want to replace those with a CGRA or an FPGA, the reconfigurable fabric would need to be big enough to accommodate all those accelerators that you would normally have and on the reconfigurable fabric, such that you can have them all operational at the same point in time. You see?
Okay, so all the ones that you would typically need at the same time, but not all the ones you might ever need.
Right, exactly.
But I guess I'm wondering, how intrusive would that be in terms of, say, an iPhone, which I presume has got tons of things in it, right?
Mm-hmm.
And how intrusive would that be in terms of the operating system and apps and communicating what's going to be required? Would it require lots of kind of redesign of abstractions and things?
Yeah, sure. We've been making a lot of shortcuts here. It was merely showing what could be possibly done. There's definitely a slew of design issues that need to be handled. Like overhead of reconfiguring is one issue. At least for FPGAs, the time to reconfigure FPGAs can be quite time-consuming. It's much less time-consuming in CGRA, for example, because CGRA, you can more think of it like a reconfigurable processor architecture into how data is flowing through the different compute units. It's more programmable, I should say, compared to an FPGA, for example. Yeah.
I have a question.
Sure.
So maybe the elephant in the room is what is AI workloads. And it's like the totally different trade-off.
Yeah, AI is a big is a
In fact, apparently AI is causing all the cloud to change their carbon footprint, that they are getting worse instead of getting better and stuff like that. And they want nuclear power plants to power
Right.
their data centers.
Yeah, personally, I'm really worried about the impact of AI on the contribution of ICT on global warming and sustainability in general. Like, yeah, all these big companies already connecting or setting up contracts with nuclear power plants to provide enough energy. It's a mess, I would say. But that's my personal my personal opinion. Okay. Thank you.